All right, let's get started. We're diving into one of the most important chapters for your JEE prep, and that's thermodynamics. We're going to lay the groundwork here, really break down the core ideas so you can build a super solid understanding right from the start.
So let's kick things off with the really big questions. I mean, have you ever stopped to wonder, why does a chemical reaction even happen in the first place? Or, why does a fire feel hot? Why does an ice pack feel cold? These seem like simple things, but they're not just random observations. They are the exact questions that thermodynamics was invented to answer. It's all about getting to the bottom of the energy that drives, well, pretty much everything in the universe.
Okay, so to tackle all that, here's our game plan. First, we'll look at those core questions. Then, I'll give you a roadmap for the whole chapter. After that, we'll get into the essential terms, our toolkit. Then we'll classify different systems, and finally, we'll wrap up by looking at boundaries and how things interact.
All right, let's jump into our first section, the core questions. Now here's something you've got to get right from the beginning. Thermodynamics is not about how fast a reaction is. That's a whole different topic called chemical kinetics. No, thermodynamics is all about possibility. It asks, will this reaction even happen? And if it does, which way is it going to go?
And that, right there, is the real power of this subject. It's not just about memorizing a bunch of formulas. It's about learning how to predict the future of a chemical reaction. I mean, think about it. Will it happen? Is it even feasible? And is it spontaneous? Can it just go on its own without any outside help? These are the exact kinds of questions we're going to learn how to answer.
Okay, let's move on and see how this all connects. Think of this next part as your roadmap. Seriously, if you understand the structure of the chapter right from the beginning, it helps you see how all the different pieces fit together. It really helps you avoid that feeling of being completely overwhelmed, which can happen with this topic.
So, the chapter is built in 3 logical steps. First up, you've got the first law. This is all about the conservation of energy. Heat, work, internal energy. Then we get to thermochemistry. This part is all about the heat involved in reactions, which we call enthalpy. And hey, quick tip, you're going to want to pay extra close attention here. A ton of JEE questions come from this exact section. And finally, there's the second law, which brings in concepts like entropy and Gibbs free energy to explain why some reactions just happen.
All right, listen up, because this next section is maybe the single most important starting point. I'm serious. Before we even think about any laws or equations, we have to master the language, the vocabulary of thermodynamics. Every single problem you'll ever solve, from the easiest to the absolute hardest, depends on you having a rock-solid understanding of these basic terms.
First term, the system. It's super simple. The system is just whatever part of the universe you've decided to study. That's it. So if you're looking at a reaction happening in a beaker, the stuff in the beaker is your system. If you're thinking about a hot cup of tea, the tea itself is the system. It's just the thing you're focused on.
And if that's the system, then the surroundings are, well, everything else. Literally anything and everything in the universe that isn't your system. So for that reaction in a beaker, the beaker itself, the air around it, the table it's on, all of that is the surroundings. This leads us to a really simple but incredibly powerful idea. The universe is just the system plus the surroundings. That's the whole equation. Now, it might sound super obvious, but trust me, this simple definition is the key to unlocking some of the deepest concepts in all of thermodynamics, as you're about to find out.
So, okay, what's the thing that actually separates the system from the surroundings? We call that the boundary. Now, this boundary can be a real physical thing, like the glass walls of that beaker, or it could just be an imaginary line you draw. The most important thing to remember is that this boundary sets all the rules. It decides what's allowed to come in and what's allowed to go out.
Okay, so we've got our basic toolkit of terms. Now let's actually use them. We're going to move on to classifying different types of systems. And this is a huge concept for the JEE, so pay attention. It all comes down to what is and isn't allowed to cross that boundary we just talked about.
This table lays it all out perfectly. First, you have an open system. Think of us, our bodies. We can exchange both matter and energy with our surroundings, right? Then there's a closed system. Imagine a sealed bottle of water. It can get hot or cold, so it exchanges energy or heat, which we call Q, but no water can get in or out, so the change in mass, delta M, is 0. And last, you have an isolated system. The perfect example is a really good thermos flask. Nothing gets in, nothing gets out. No mass, no heat. This is definitely a great slide to grab a screenshot of for your notes.
So let's take this idea and think big, really big. What about the universe itself? If the universe contains everything, what's outside of it to exchange stuff with? The answer is nothing.
This leads to a really profound conclusion. The universe is the most perfect isolated system we can imagine. And that idea, that's the foundation for the first law of thermodynamics on a huge cosmic scale. It means the total energy of the universe is constant.
Okay, now let's go a little deeper on those boundaries we mentioned, because here's a pro tip for your exams. Understanding the type of boundary in a question is often the secret key to solving it. The boundary's properties literally tell you which formulas you're supposed to use.
So first, we can talk about boundaries in terms of heat. You've got an adiabatic boundary. Think of it as a perfect insulator. No heat gets through, so Q is 0. That thermos flask is a great example. The opposite of that is a diathermic boundary. This one lets heat flow freely, just like a metal pot on a stove. And you can bet that the people who write your exams love to ask questions about this difference.
Next up, we can classify them based on whether they can move. A rigid boundary is exactly what it sounds like. It's fixed. It can't move. This means the volume of the system is stuck. It cannot change. And that is super important because if the volume can't change, no work can be done. On the flip side, you have a non-rigid boundary. Think of a piston in a cylinder. It can move up and down, which means the volume can change, and that's how you get thermodynamic work.
And just to round out our toolkit, there are a couple of other ways to think about boundaries. Is it real, like an actual wall, or is it imaginary, like just the open top of that cup of tea? Is it permeable, meaning mass can pass through, or is it impermeable, meaning mass is blocked? Knowing these final details helps you paint a really precise picture of any problem you're trying to solve.
And all of this brings us to what I think is the most important takeaway from our session today. Look, thermodynamics is a subject that's built on pure, simple logic. If you can truly master these fundamental definitions, system, surroundings, boundary, all of it, then even the most complex-looking questions start to become simple. But if you don't have these basics down, even the easiest problems will feel impossible. So think about it. Which one of these ideas are you going to really lock down